Hello everyone on YouTube. Well, I'm Leo. I'm one of the RIS 2024 scholars at CMU with more than 40 other amazing people here. And today we'll have our first session of the RoboLaunch Outreach Initiative. And it's my pleasure to introduce Professor Zeynep Temel. Zeynep is an assistant professor in the Robotics Institute at Carnegie Mellon University, where she leads the Zoom lab. She's interested in bio-inspired solutions to increase mechanical intelligence in robots and robotic components. Her goal is to create robots that can mechanically conform to the environment or objects that they interact with to alleviate the need for high speed, high accuracy, and high precision controls. To achieve that, in her research, she develops compliant mechanisms for manipulators and robots, which is classes that focus on bio-inspiration and unconventional robotics, and engage with the community to increase interest in science and engineering. Zeynep obtained her PhD in Mechatronics from Sabanci University with Professor Serhat Yesilyurt. Prior to that, she obtained her master's in Mechatronics from University of Siegen and her bachelor's in Mechanical Engineering from the Instanbul Technical University. Zeynep, now I hand over to you.
Thank you so much for the introduction. It's great to be here with all of you, and hi to the people on YouTube. This is my first time doing a live YouTube thing. I feel like I'm an influencer now. Welcome to my channel. Okay, so how can we make it even bigger, like this screen here? Is it possible? I think it will be better for videos. I think YouTube should work properly. If someone can confirm that.
Yeah,
okay, cool. Okay, so adaptive robotic systems using embodied intelligence. What does it mean? Is everything okay?
It's in Portuguese.
Oh, it's in Portuguese? Okay, well, we have an international group here. Okay, what does this mean? We can just keep going. Yes.
I'm guessing that means like a robot is placed in the environment and then it'll learn about the environment and adapt to it, or it's specially equipped for certain environments.
Yeah, you use the keyword learn. So I'm not doing learning myself. I usually collaborate with people. Full disclosure, I'm a different kind of roboticist. Maybe I shouldn't actually define myself like that. But as you heard when Leo told about my past, I'm a mechanical engineer, so I really don't like sitting in front of a computer and code. I like going to lab and build. In fact, I have a terrible relationship with computers. My brother usually does all the computer things for me. I am a person carrying my toolbox everywhere. So, okay, so just take learning out. Everything you said is correct. So this is what I'm trying to do. Although this is again a bunch of like buzzwords. So you can also call me out. I like to be challenged. I like to, hear about challenging questions. Okay, so we started with this in robotics, right? The aim is to find dirty, dull, and dangerous tasks for humans and then replace the humans with robots so that they cannot they can be done, these dangerous tasks, this dirty task can be done by robots. So this is like one of the, the impressive examples of how we use robotics, an assembly line. We have been interested in this for years and years. What are your interests for robotics now? Are we still interested in making robots for this? Or what are the dirty, dull, and dangerous tasks around us? Yes.
I think industry robotics is still a growing field, but we also have mobile robotics, which is allowing us for new interactions, especially for dangerous jobs.
Okay, like what?
Or search and rescue.
Search and rescue.
Mining.
Mining. Yes.
Underwater welding in the oceans.
Sure. What else? Yes.
Space exploration.
Space exploration. Yes. What else? Yes.
Exploring nuclear fallout sites.
Awesome. Okay. Who can name one of those robots? Spot. Okay.
Eels.
What?
Eels.
Yes. What else?
Curiosity.
Okay.
Spelling robot.
What?
Spelling robot is from a Brazilian mining company.
Okay. How many of you saw those robots? One, two. Which one? Spot?
fields.
Yes, okay.
Robotics.
Okay, cool. Okay. Probably all of you, or the majority of you, have seen this stuff, right? This is a robot that we actually see around us that we can actually purchase, go to a store and purchase. You don't even have to go to a store, you can buy it online, right? And then it will be delivered to your door. So we became more and more interested in these kind of robots that we can actually interact with, that we can play with, right? That we can actually like open it up and then see what's happening maybe inside. Cool, okay, that's good. Another example, I was watching a show on TV in a hotel room, and then saw a show called The Toys That Made America or something like that. And then they were showing this, Transformers. They're coming back, I think, or they came back already. I'm not familiar with what's going on at the moment. But so I remember these toys, and look at these toys. They're like super like metallic, like bulky, technological, like rigid. Oops. Okay, sorry. Wrong. I was very excited. Okay, so that kind of toys. And these were the toys that we were interested in playing for a while. And this kind of toys have inspired us to do robotics. What about now? Yes.
Now it's less on toys and more of just science fiction and seeing what we're able to do now and interested in what we can actually do in the future.
Okay.
Because a lot of robotics companies rely heavily on social media to get their name out.
Okay. Cool. What else?
And there's always a fashion of wanting too much success, like examples of
Okay. What else? Yes.
I mean, people might be inspired by the Roomba in their house, but I mean, it seems comparatively a bit uninteresting. Like,
Roomba is less interesting than Transformers. What is more interesting than Transformers?
well, I mean, to like a kid.
Yeah, for a kid, yeah. What? No way.
Video games.
Video games. What else? So they made the toy. When they made the toy, they also made the comics series. They also made the TV shows, like the cartoons and everything, and movies. And now the movie that we are watching, or that is actually making companies earn money, sure, this, but also this. Right? Is it cute? Yeah. Do we like it? Yeah. Does a robot have to be cute for us to like it? No? Yes. Okay, nice answer. So I am kind of like, opening this up with questioning. Like, what are we doing in robotics at the moment? Are we still interested in these? Or are we still like, are we now shifting our interest in these? Or with the, developing technologies, material science, like controls and learning and everything, are we actually expanding our view of robotics and what a robot can be? Just, a food for thought, think about it. I'm very happy to talk about these kind of, questions. Okay, let's play a game. I think people on YouTube can also play a game. I know it is a technology-free time. Just for these 5 minutes or like 2 minutes, I'll ask you to pull up your smartphones and play a game with me. So if you had a robot that could do anything, what would you have it do? I have a typo there. Single words, or if it's multiple words, please use dash, because if you say like, give me an example, walk with me on the road, it will be like walk with me on the road. So it will appear like that. So did everyone capture this? Good, I need to start it, I think. Okay. So you can respond as many answers as you want. This is all anonymous. We're just playing a game. Laundry, do my chores. Laundry. What is this like face? Is it attached to something, that face? Was it supposed to attach? Clean the bathroom. Snow plowing. Well, we have now lawn mowing, right? Folding laundry. Clean my bathroom. I assume it is like emotional support somewhere. Make bad. President? You want a robot to be a president? Very, very creative. Water the plants. Yeah, we like the plants, but watching the plants is like much more. Sing. Do you know that we actually have a robotic pipe, the Scottish pipe, that is a robot that comes out in the graduation ceremonies to play. So we actually did that. I mean, someone did that. Okay, so for those who wrote homework, not to encourage you, but now we have ChatGPT. So kind of. You cannot longer, okay, can you? Oh, no, I can see it here. You can see it there. That's very interesting. I don't know what happened. Oh, no.
Sharing screen.
What's that?
Is that because when you're sharing screen, you're only sharing the presentation?
Maybe. I don't know. I have no idea. I can see the responses here, right, and clear for everyone. Okay. So.
It says at the bottom, share the entire screen.
Where is that?
Never. You can show.
What? I don't read it. Start the presentation to see the live content. This is the presentation.
For screen share software, share the entire screen. I think if you need to share not just the presentation, like overlays.
Oh. Do we really want to do that now? We already saw it. It's fine. Okay. So you said laundry, right? And then cooking. What else? Wait. I cannot do it now. My cook and laundry. Great. This is what I thought. That's why I'm bringing this photo for you. I think I played this game for 4 times now, and the answers are cooking, laundry, basically chores, the things that we don't like doing, I guess. So we want robots to work in that environment, right? Okay. Do we have any robots to work in that environment to cook? No. This is a big thing nowadays. I saw it in a bunch of places, actually agriculture, like picking up fruits, like gardening, you know, that kind of work. We really want robots because it is like under the sun, really like not fun work, you know. So that is something that is coming along. This is another field that we want robots to work in. We actually, one of my colleagues did a survey recently saying, asking like in a nursing house, you know, what would people need to the patients? Like what kind of, you know, things they are missing? They are missing human interaction. So if we actually, and especially now after a pandemic, if we can take some of the tasks from nurses' plates, not to replace them, but actually to give them a chance to have quality time with patients. They can actually sit down with patients and talk to them, or like, you know, solve puzzles with them, while the robot is taking care of preparing a care plate, for example, a care tray, right? And obviously, you also have search and rescue. This is what I'm very interested in because of the, you know, my background. Okay, let's take number one. If I make a robot that can work in the kitchen, would I solve the cooking problem? Why not?
Not necessarily a problem, it's more just to streamline the honest tasks.
Okay, let's say I figured it out. It can work in that kitchen, like, yes.
There's an infinite number of dishes, and so you need to be able to do anything.
Okay.
It's a really general term.
Would also have to do grocery shopping.
Grocery shopping, okay. So let's say I made a robot that works in this kitchen. Let's say this is my kitchen, yes.
That's just the one kitchen.
That's
Every
just the
other
one
kitchen
kitchen.
is different layout.
If I give it to you, would it actually work in your kitchen? Who knows, right? So the thing is, we can make a robot, it can learn whatever, you know, like be very competent. If it doesn't have the right gripper to open the drawers, which is different there, different here, different there, different there, right, it will be useless. So how can I make robots more adaptable mechanically so that they don't have to learn these things, but they can just like, you know, if I have a handle that can actually like pull, push, grasp, like whatever things, right, mechanically. Would I actually solve, would I make the robot sleeker, right? So I'm basically giving the load to the mechanisms instead of the controllers. Is it possible? So that's the idea behind my research. So where do I look at how can I make it to the nature? Obviously, we see a lot of examples that robots are, that animals are compliant, so maybe we can do that. Like cats, I like cats, they can basically fit anything because they're fluids, right? I look at, you know, different animals underwater. Octopus actually is a great example. They can stiffen their limbs or like relax their limbs. They can do a bunch of different motions, and they can fit in like this glass, this bottle, and then also cover a huge area, a huge space. And ants are my favorites because they can, you know, jump, they can smash, they can just use their mandibles as manipulators, but they can do it in very different environments. Put them on sand, put them on rigid surface, put them on leaf, it's fine. They can just work it. So how do I make robots that can actually change their shape or adapt their shape to the environment, become bigger, smaller, or change their stiffnesses, or work in different, you know, surfaces? Is it possible? We are trying. This is my lab. You will see some familiar faces here, and I won't go through every single one of the projects. I will just play some videos as much as we have time. I think I can make it very quick. Do you have any questions so far? Yes.
So, specific to the kitchen task.
Mm-hmm.
What is the difficulty in modeling that looks like a human hand? What do you plan with?
Oh, humans are animals. But you can look at humans too for the grasping things, like, sure. But is it actually, there are many hands, there are some hands out, like you can buy them, right? Is it the best way to approach it? So that is how I will challenge my like bio-inspiration versus biomimicking thing. You can definitely look at a lot of things. Like we are looking at us all the time, making humanoids. Is humanoids the best answer? Are we in our final shape? Any other questions? Yes.
Earlier, you mentioned loneliness, and I wanted to ask, like, what qualities do you think a robot could have that makes humans attached to it?
You mean the healthcare robots?
Healthcare robots.
Oh, okay.
Yeah.
Okay, we have some robots in the background. Which one would you be attached to? I don't have an answer. I have a personal answer. That one, why? It's the cutest one. Yes, I want something cute. Like I'm very attached to my cat. I don't know why. Maybe we can check why and then see if the robot can, you know, is it the fur or is it the annoyance? I don't know. Like, you know. The other thing is that I'm attached to my robots, like the robots that I understand, the robots that I can actually fix or upgrade or change its shape and, you know, or control. So that might be another thing. So I don't have a good answer, but that is a good question. So I think, okay. There was another one. Yes.
Do you aim to make like universal manipulators, or do you think about like ways to maybe like switch out end effectors or something? Or yeah, what are your kind of over?
I don't know, either, both. So you know, making something universal is very difficult, right? So we are pretty developed, right? We still need a screwdriver, right? And I don't know why we designed it that way. I mean, there's a reason that we designed it, you know, screw and screwdriver. So we still need a screwdriver. So I'm not against using tools. That's not what I'm after. I think I'm more like, we want a robot to be like do everything by itself, I am kind of questioning that idea. Does it really need to? Like, because we can't do everything by ourselves, or animals cannot do everything by themselves, right? They develop different strategies. How can we also put those strategies to robots? Okay. There was one more. No? If not, I am moving. Okay, let's start with the combined manipulation. So these are Delta robots. Delta robots are widely used in industry. They have like 3 actuators. That means they have 3 degrees of freedom, but the actuators are connected to the end effector with parallelograms, which makes the end effector parallel at all times to the surface. So they can move in X, Y, and Z, but they cannot do any rotation. If you can add 1 more degree of freedom at the very tip, so they can have the 4th degree of freedom, but usually the mechanism is 3 degrees of freedom. They are widely used for pick and place applications where we don't want humans to touch things to be pick and place, like medicine, food, food packing, medication packing. They are widely used. The good thing about them is that they are super fast, super precise, very accurate, because they don't have any mess in the moving parts. All the actuators are in the base, and the moving parts can like just beams, like linkages basically with joints and links. I don't know why it is. Maybe it is because of Zoom. It is like choppy, but you get the idea. So these are widely used, but they are usually large systems, right? And then rigid systems. So I was looking. If you look at nature, not everything is as rigid as this. So my first inspiration is like, if I can make it smaller, what would happen? If I can make it softer, what can happen? So this is what I did when I was a postdoc. This is a much smaller version of a Delta robot that was made by layer manufacturing techniques, not 3D printer. You basically sandwich rigid and flexible materials to create linkages. And then you put together, the pop-up cards, right? You basically have the same philosophy for designing these kind of robots. So we designed these robots. If you notice the triangles underneath these robots, those are piezoelectric actuators. They can bend both ways. The good thing about piezoelectric actuators are they are extremely fast. So with that, we reached super high speeds, which was very nice. And it is super small, like you see the penny size, right? What can we do with it? So I usually don't think about my applications at first. I like to play and then discover. And then I'm like, oh, now I have to find an application for this. So we thought that since it is very fast and compact, it might be a great tool to put inside handheld surgical tools to compensate surgeons' tremors. Because if you imagine yourself sitting in a eye doctor's chair, and the doctor is approaching you with a needle, with this shaky hand, I think I would run. So you don't really want the needle to shake, right? And then we show that this actually compensates different people's hand tremors in a very good way. So I was working on this when I was a postdoc, and then I came here and I presented this work, and my friends were very interested in this. And then they said that, hey, Zeynep, we want to make fingers using your Delta robots. Because things they are very fast and accurate and precise, and they're very tiny, right? So they can actually do tasks like we will do pretending now. They can actually take a pill bottle from the bag of a sick person and then open the bottle, right? Many fingers, and then take one pill and then feed it. So they said that we want to make strong enough end effectors, manipulators, to open the pill bottles, right? And then dexterous enough to manipulate a single pill, and also safe enough to interact with humans. So how can we do that? So this is one of the big projects that is in my lab. So I'm just skipping this because we already talked about this. I thought that the simplest thing would be just 3D printing using soft materials we call TPU. And why not start there? And that's what we did. So these deltas have linear actuators. There are two deltas. They work like fingers, right? Think that you have two fingers, so they can actually do a lot of different manipulation tasks. So they can just pick up a card very sleekly, right? You can change the fingertips. They can grasp the grape, and then they can rotate it to get from the stem, so they are pretty strong in that way. And they can interact with soft objects too. It can just roll a dough. It is very choppy, so the video is going very slow at the moment. It's fine on YouTube? Yeah, probably.
I think it's probably projection.
Projection?
Yeah.
Okay. I'm glad that it's fine on YouTube. So, or, we can roll it off. Okay, I will move a little bit quick. They're also very soft, so we obviously did the same, what everyone does, hit the robots with the rigid objects, because that's a trend now. Nothing happens because they can come back, it's perfect. What are the problems with this? So this is a single delta module. What can be the problems with these? Yes.
Since you need more force actuated, the actuators take up more space.
Sure. It's pretty compact actually. We wanted these to be longer, but we also have very small actuators. But I can see that. What else? Yes.
Precision,
Yes. Since it is soft and we want it to be soft, we cannot really control it properly using kinematics. So what do? We use learning. So that's where I collaborate with other people like Professor Oliver Cromer to help me to control these actuators, these manipulators precisely, or as much as possible. The other thing is that these soft materials will change their behavior with time, with humidity, with temperature. A lot of things are, changing in our environment. Would they actually adapt to those changing, parameters? So when we did that, we were like, okay, so we built one module, we use it with two fingers, cool, but we want something bigger and we want to study this multi-finger manipulation thing. So can we make 4? And yes, we can make a 2x2 delta array module and then make 4. Why not go bigger? Let's go crazy. Can we actually make 64? And then we are like, yeah, sure, why not? Let's make 64. So this is the delta array setup that is in my lab. That is pretty huge, but it is a great setup for us to study multi-agent manipulation, multi-array, array manipulation. And we show that we can do a bunch of multiple tasks with these kind of arrays. Since we have 3 degrees of freedom for each robot, we can do rolling, we can do moving, pushing. We can also raise some of the robots to create a wall, to align things, right? So this was very, we were very excited about this. And then we wanted more because you said you want this cook, right? I like pizza. So I said, can this actually work on preparing a pizza dough? I will just put the blob of dough and then it will just open it. For that, we need to turn it upside down. And that's what we did. And now we have a camera in the bottom. All the robots are upside down. And we are working on how to actually manipulate objects using this multiple array. So this is a big multi-agent learning problem that we are working on. Stay tuned. If you know Sarvesh, do you know Sarvesh? Yes, if you don't know Sarvesh, go meet Sarvesh. He's a great guy. He's working on this project and he would love to talk about this project with you. Yes?
I was wondering how long it took to build the whole system and then also how much the total cost.
I don't know the exact time. It took shorter than we would expect because we were surprised that Sarvesh built it very fast. We were like, oh, we have it already. The big thing was Sarvesh started during pandemic, the things delayed, the deliveries delayed, right? So that was a problem. The cost, so I will say $80 per actuator times 64, maybe 100, so $10,000, let's say, which is not cheap. We are aware of it, but this is a huge system that we don't want to be in the this turned into a research project now, like not for like immediate future applications, right? So for research project, actually $10,000 for this kind of an array is not bad.
Sarnesh was on a panel for them 2 weeks ago, so they got to be in this room.
Oh, yeah? Okay, cool. Yes. So you met already Harish. Yes. So, okay. So this is the, recent things that Harish is working on, like which robot should actually go down to manipulate this, block and then push it forward. So this is like, there are multiple, there are other things, but we are not done with the project yet. So if you want, you can talk to him. So another thing I will quickly talk about is that since I like working on small things, I was like, hey, this Delta array is so cool, but I want something smaller. Can you build me something smaller? So this is Zillan's work. Zillan is not in US. I think she'll be back soon. So I will encourage you to talk to her too. So she said, okay, why don't we build a hand using Delta robot? And this is what we did. This is a 4 Delta robot, like 4 Delta robots. There are coupled actuators in this one, not in that one. I think that one has 12 actuators. This one has only 5 actuators. So we configured them in a way that we can couple the actuators. So it is lighter. And then, we studied the motion if we can still get the same force or workspace from these manipulators. So that's what we started studying so that I can bring robots to wherever I go. And we show that we can do multiple tasks like this one. It is also pretty strong. You can see now like Zillan is applying a good amount of force, but the robot is not giving the key. Also, Zillan built a teleoperation setup. This is a lead camera over there that is watching Zillan's hand motions, and the robot is basically mimicking what Zillan is doing there to open up a soft object. In this case, a rope. I think also like opening up a cap bottle. Yes. 15 minutes. Yes. Yes.
Yes. I've heard fingerprints are useful for humans for like grabbing paper.
Yes.
How did you all approach that challenge?
So we also, do you see like they are different color? We are actually trying a lot of different fingertips, like either using even softer materials or like some patterns. And we are now working on embedding sensors in the fingertips so we can have the full system like as a robotic manipulator. So yeah, good question. It's definitely important. Okay, so, or folding, cloth folding, we are working on it. I'll just move fast because we are already at the 15-minute mark. The other thing that we can do is, oh no, this is broken. We developed an educational tool using Delta robots. It is all 3D printed. This is less than $50 so that actually students can, why am I fixing it? Maybe you can fix it. So students can learn how to use like robots or any subject robotics related. So the end effector can be changed. This is a, what is that? Like an iPad thing that, I was playing with. Like the parts, this is all like on GitHub. If you're curious, you can check. This is actually a risk student's project, Sam. He made this user interface, the design, the fabrication things, all the files are like, you can find and play with it. And again, everything is commercially available, so you can actually build your own. This is pretty broken. I'm very sorry about that. But yeah, so I'll also pass it around. Feel free to open the cap. You can see what's inside and play with it. Okay, so I only got through one project and I have a lot more to talk about, but we are already at 10-minute mark, 12-minute mark. So I will stop there and see if you have any questions. I can keep showing videos. Yes.
It seems like you use a lot of like creativity and play to come up with ideas. Like
Yes.
How do you actively incorporate that to your design process, or are you just like really into it and then it just kind of like happens?
Both. Like I really like watching things around and then how things happen. And sometimes when I play with this, right, like something, I just start designing. And then I'm like, oh, wait, I should have done this way because it might work better. Or why am I not doing this way? And sometimes I cannot see it because I am so much into it. Sometimes other people can say like, hey, can you explain this to me? And when I talk to them, I'm like, oh, wait, I think I should do this way, you know? Like a lot of things. But I really like the play component in design because that basically breaks the walls that you put for yourself, right? So you obviously need to have some constraints or requirements, but like if you also limit yourself with respect to materials, with respect to actuators, with respect to design, because things have been done in some way for years, I think that limits the creativity. But I just want to go and play, and sometimes, most of the time, really cool things happen when I play. So these are PuzzleBots. I will also give them for you to play. They can attach to each other in two different ways. If they attach sideways, this is like rigid connection, so they become a block. If they attach like this front and backwards, this is an anchor, soft anchor, so they're flexible. So we can adjust the stiffness of the configuration of these robots. I'm showing this because this is also not the PuzzleBots, but that climbing mechanism is a risk student project, James Clinton. And he is now, I think we submitted the work. We are waiting for the results. I don't know why it doesn't play again. I want it to play again. Yeah, so all these mechanisms, he actually designed to overcome the obstacles in different terrain. So, any other questions? Yes.
What do you think are the hardest bio-inspired qualities to mimic? So I imagine like an ant jumping is a little bit different than an octopus collapsing in on itself.
Good question. I would say the distributed system aspect, right? So we usually put a camera on a robot and then expect it to do everything. But if you look at our cells, we are full of sensors, like full of sensors, right? And it is not only touch sensor, it's also temperature sensor or humidity sensor or whatever, right? That we have. Actually, it's, I think, humidity sensor. So I think that like an octopus does that, but how? Or ant does that, but how? Because it actually has a very limited compute, right? And very limited physical ability. But sometimes with all those sensors, they can just, you know, make it make sense, all those data, and then do the action. I would say that, but I'm not very confident. Yes.
So you seem to be using a lot of the products of evolution as inspiration. Have you ever thought about using evolution itself as an optimization paradigm to either design the robots or to design the control structures for the robots or something like that?
Yes, I have a friend in computational biology. We will start hopefully working together to explore that. That's a great aspect. Yes.
So if you think of aircrafts, for example, aircrafts fly, but they don't fly the same way as birds fly, for instance.
Yes.
So I was just curious, can you give like some other example that you think is interesting, where you have some by inspiration, but you kind of change the design a bit to make it more efficient?
So that's not my work, but you should check Elliot Hawks from, I think, UC Santa Barbara, if I'm not wrong. So I follow him. He does great work for his jumping robots. So we usually think that jumping robots have to be small because they have to be lightweight to, you know, to get to certain heights. Especially if you are using traditional springs, meaning not combustion, right? We can also argue like a spaceship is jumping, right? So forget about combustion, just, you know, springs, because this is what animals do. So his robots are relatively bigger And I don't actually know any animal that big that can get to that extreme jumps. Because he basically figured out a clever way of organizing springs in the body of the robot. So that's one thing. The other thing, Mark Katkowski from Stanford University, most of the animals that we see are like moving on the walls or ceilings are small, but he actually developed this sticky material that you can even wear in your hands, like, you know, as gloves and in your feet, and then climb on like a Spider-Man basically. So yes, does it answer your question? Yeah. Any other questions? Yes.
I wanted to ask, how often do you travel around the world to look for inspiration?
Not often enough. So conferences help. That's why I like academia. So we can travel different places. But you really don't need to travel further away. I don't know if they built the pond, where the Westinghouse statue is, and like at the entrance of Shelny Park. But I usually take my students there to collect insects, and then we just observe different behaviors. Like when, you know, something that I really want to do is the ladybug wings. Like everybody explore, like a lot of people are exploring that, but still we didn't do an aircraft and like a machine using that, you know. There are a lot of things, like you don't have to go far away. But obviously it's fun, like trapdoor ants, I didn't see them around there, more in the south, I think. I might be wrong. Yes.
How do you decide where to take a research project once you finish a portion of this? Like, for example, like this project, where would the next steps be?
For this one, what do you think?
Just having it go into more challenging terrains and see what appendages would be useful there.
Sure. Yeah, that's obviously right, a natural path. I think I want to make it 3D. Yeah, I don't know, whatever is interesting. I don't think there are wrong answers there. If you have a valid research question, I don't think there are wrong answers there. So the terrain thing, I will just show one more video. So we basically, wait. So this is a rough terrain, right? And we were first using these rigid connections between robots, and the robots stuck because of these rigid connections. They didn't have flexibility and they couldn't finish the course. And then we introduced these flexible connections, and they were able to basically move a lot of different terrains with different heights of obstacles. So yes, but this is still limited, right? So yes.
I definitely see with the adaptation to different terrains, I definitely see a lot of possibilities regarding rescue missions in order to build terrains. That possibility that you're currently considering, of course, it would need to be a bigger size. But is that something or for recognition or stuff like that?
Why does it have to be bigger size?
I mean, actually, no, it would because I see two ways. Either it could be done as a recognition to like see the area, but also like to lay ground for like different like equipments and everything. It's so versatile. You can like travel and have a lot of things that could help rescue stuff like that.
So this is a recent project that I'm working on in collaboration with Laura Blumenschein from Carnegie University and Nilsa Martinez here at CMU. So I am more interested in the small robots, right? And I think small robots can actually be more useful in the search and rescue field because they can get into small places, they're faster, they're quieter, right? There are many advantages. But they have a tiny little battery, right? They die in 30 minutes, so they're actually useless. But they're cheap, and we can make them mini, right? So they can like be everywhere. Like they're trade-offs, right? And Laura is building the soft-growing wine robots, right? The thing is, for all of us, for all three of us, it is so annoying that we still don't have a functioning search and rescue robot. That is like, you know, that can actually do search and rescue missions. So we were talking about that, and we were laying out the limitations of these robots. So soft robots are great, but they have limited like turn capability. They are very slow, right? So there are a bunch of things that we don't also like, they have limitations. So we were like, hey, why don't we make robots working together? So the soft robot can deliver the small robots to the field of interest. And like, small robots can explore wherever it is. So they don't have to waste their battery to go to the places, right? And then they can also help the flying robot to take 90-degree turns or very sharp turns, like pulling or pushing or splitting the diameter, basically buckling, right? And if flying robot has like charging stations, the small robot can go and charge themselves maybe after 30 minutes and then continue their mission. The small robot can be the eyes. I don't know. We are working on it. Yes.
So Ryan kind of had my exact question about the evolution thing, but like, do you have any examples of robots that can either like self-replicate and then change their mechanical parameters through evolution, or just like adapt during their lifetime to change mechanical parameters, not just like learning parameters?
Not that I know of, but there are materials that are, let's say, conductive and stay conductive even if we like punch them. Or there are materials that we cut, like that we can cut them, right? They're the two materials and then put them together and then they can like merge into one again. So there is definitely work going on in the material science domain, and actually most of them are happening here at CMU. Some of them are happening here at CMU. Professor Kamal Majidi from mechanical engineering, Professor Mohammed Islam from material science. So they are all working on this. So once we have that technology, we can think about like embedding, again, how can we distribute the robotic components into those materials and then make them robots, right? Turn them into robots. So not that I know of.
Well,
I think I'm time, right?
Yeah.
It's time
so
for me. Okay.
let's please. Thank you very much for coming, and thank you for bringing all those robots. This was
Yeah.
And for everyone on YouTube, thanks for joining as well. I hope you enjoyed the talk as much as us. And if you're still there, we have an upcoming talk from Professor Zeynep Temel in the same YouTube channel, so we can just switch links. And I hope to see you. Well, I will see you for sure, but I hope to see you there on YouTube as well in the next talks. Thank you very much.
Thank you. One thing, please do not hesitate to reach out. Also, people watching online, I'm very accessible online. You can find my email address and stuff. So I'm happy to chat.